Welcome back. Problem 4. We are going to work in the next two exercises on the series presented on page 23 in the book. Here we have them. I anticipated this, so part of the work I did studying the section was to make a Maple file with the series, reproducing the computations in the section. So I start defining part of the series up to set to the, we'll just run it so we can work on it if that should be needed. So up to 10th power, the system is obvious. So then I differentiate it, and later on I discover that I only need powers up to set to the 6th, or rather I took as many terms in P needed to get the coefficient to set to the 6th of the final equation correct. We square it and square the derivative and define PM2 as the powers, the terms all up to set to the 6th. This the part of it we call PM2. Then we square P and expand it and collect terms of set. And again, this part is called P2. We do the same with P to the 3rd. I realized I could use series, and this only gives to the 2nd order. This gives to the 8th, but we need these, this from here and up. That's defined as P3. And then we realize, as they did in the text, that set to the -4th occur in P2 and nowhere else, meaning it cannot participate in the final equation. And then we write up the equation with the coefficients A, C, and D, and collect terms of set. And we see here A equals 4, and C equals, what is it? Oh, then we have to multiply this by 4, so that becomes complicated. I think it was 64, etc. This equation gives C, and the constant term here will then give D. The next term here, z squared, introduces G8, so we can find G8 from that, G10 from this, G12 from this. And that's what I do here. I solve the equations with respect to A, C, D, and the G's. So we get A, C, and D, and G8 exactly as problem 4 states. And then as well as that, we get G10 and G12. And noticing the weights they talk about, can think of it as the dimensions of the axis of the lattice. So 10 has height 10, so we get a product of G4 and G6. G12 has height 12, so these combinations are possible, and so this turns out to be the coefficients. Now G8, exactly as it's stated in Now where is grid? Here in the problem. So I have prepared myself for this by writing up the Weierstrass P function and its derivative, and I think we could do with only powers up to 6. So we take the second derivative, minus 2 times minus 3, 6, d4, 20, 60. d6, 42 times 5, and the squared. We'll just do the lower terms. And the double product of the two first terms, these terms, that is 6d4. And the next double product is 10d6. And then set to the fourth. We'll get one from this one squared, that term squared, and the double product this with this. That's 14 g8, and we can verify that the height or dimension of these terms are 8, so it's 4, 6, 8. So we need to use the equation. We'll just verify the first terms. The double derivative should equal 6 times this guy. Agreed? Not agreed, that gives 36. We have to subtract 30, so that's all right. And a factor 6, so nothing new there. And then these two now watch this. It should be to the fourth. That's z squared, and minus 2 times, yeah. So the double derivative equals 6 54 d4 squared and we 14, we have to multiply that. That gives 84. So subtracting 90 here gives 220. So we can divide by 9. That gives 13. So I end up with far from the right expression, not far. So, what has gone wrong? Have I missed a term? Or is it a very simple algebraic error I have committed? We can go backwards and say the right is 3/7. So if this is 14, then this should be 230 what times 9, 230, and what is it? 14 times 9, 235, no? Well, it seems I'm unable to divide by 9. This gives 14. So it was a very simple. 14, so we divide by 2, and then we get the right result again. So that was problem 4, and it's interesting that using this equation is much simpler. So that's nice. Well, bye for now.